we're going to be talking about waves. Perhaps not that kind of wave. But maybe that kind of wave. Did you notice that the people in the stadium, they were moving up and down, but they weren't moving their seats? This is a good description of what a wave is. It moves energy. It's a way of transmitting energy, but not matter. The best way to demonstrate wave behaviour is using a slinky spring. There are two types of waves that we're interested in, a longitudinal wave and a transverse wave. But what does that mean? It's better to see it. So have a look at this. This is a nice slinky spring. Oh, you can see that there. Now, when I vibrate the spring, I want you to notice that the spring moves a bit, but it doesn't go down there. So if I vibrate it here, a pulse will go down there. I'll do it properly from over here, watch. Okay, so I flick it and a pulse moves down the spring. So what's really happening is this bit is bumping into this bit, bumping into this bit, bumping into this bit, bumping into this bit, and it goes on all the way down there. This bit of the spring doesn't end up down there. If it did, it would look like that, wouldn't it? We'd just be movement, and that's not a wave. So it's like we were talking with the Mexican wave. The metal doesn't move. Well, it vibrates, but it doesn't move in the direction of travel. But the disturbance that I've made to it sends a pulse in the direction of travel. Okay, so let's have a look at that. So I'm going to disturb it by flicking like this. But I'll do it from this end so you can see. Okay, so I'm going to flick it, and I flicked it this way, and a pulse goes down there. Did you see it? By doing this. It's a compression wave, and you can see how it's compressing as it goes down. This is how sound works, which should be of no surprise to us, since we know sound needs a medium to move in, air, or solid or liquids, but we're used to air, speaking into air, and it's air particles vibrating, hitting the next one, hitting the next one, hitting the next one, and travelling down. If if the air from my lungs went into your ear, that would be weird, and it would all just be me blowing in your ear, wouldn't it? So it wouldn't be sound. So this is a longitudinal wave. It goes a long way down. It's a sound, like a sound wave. So did you notice something else though? When I was doing it, it sort of came back. Watch. Oh, a bit bigger. Did you see it? It came back. It's reflected off the end. It reflected off this end and it reflected off that end. And that should be no surprise to us either, because we know that sound reflects off other surfaces, like off a wall when we're talking, and echoing off a cliff or something like that. So that's a longitudinal wave, where the disturbance, which was me flicking it, was in the same line. It was parallel to the direction of travel, which was down the slinky that way. Now the other type of wave, the second type, is more interesting, and it's different from this, in that the disturbance is at right angles. I'm going to disturb it, I'm going to move the slinky at right angles to the direction of the wave travel. You'll see what I mean when I do it, watch. So I'm flicking it up and down, that way and this way, and you see a pulse go down and come back on the other side. It reflected again, but in a different way. Watch. There it goes, and it comes back. Did you see it? So I disturbed the thing this way, the pulse travelled that way. So I disturbed it perpendicular at right angles to the direction of travel. That makes it a transverse wave. It bends both ways. It goes up, it goes down. And if it goes down the slinky. And when it came to the end, it came back. But did you notice it was on the opposite side? So for you it was going down, then it came back on the top as it went along the other side. So it reflected it by flipping it. Now this should come as no surprise to us because we're all used to light doing this when we look in a mirror. So we look in the mirror and we see our reflection, which is flipped, it's the opposite way around. And this is why it's bouncing off, but it's changing phase at the other side, comes back on the other way around. So transverse waves can reflect, we've seen that. Their disturbance is perpendicular to the direction of travel. But something else can happen as well. We can set up a standing wave. That's what we're going to do now. So I'm going to wiggle the slinky at certain frequencies, frequency being how quickly you can do it per second. And I'm going to send a wave down. It's going to reflect back. But the reflection coming back will meet the wave going down. So something will happen. Watch. Interesting or not? It just looked like the whole slinky was just wibbling about. It was like wiggling about like a sort of a snake. If I do it at a higher frequency, watch what happens then. It's a standing wave. It's called a standing wave. The reflection is interfering with the original pulse. So we're getting points of constructive interference where the amplitude, that's how pokey the wave is, the hill part of it, the crest, is bigger, and then we're getting bits where it's cancelled out, and so there are these stationary points, these nodes along the way. Now if I wiggle it at a higher frequency, we might get a bigger standing, or more peaks and troughs in our standing wave. Let's try it. I'll try it again. That's about as wiggly as I can get with my slinky. So hopefully you've seen a few ideas there of the transverse wave is this sort of wave shape, isn't it? I mean, come on. And we can see it on the slinky, but we can also see it on a string. Now strings are very important. We use strings in guitar strings, violin strings, piano strings, and that sort of thing. And if we vibrate them at the right frequency, they will set up standing waves. And those standing waves we can use in music and all sorts of other things. So we'll have a look at, I'll get a string out and we'll vibrate it with a frequency generator and see a standing wave on that and look at the attributes of waves in a bit more detail. This is a frequency generator. It's providing a voltage to that vibrator on the right, which is going up and down once a second. That's 1 hertz. It's making the string go up and down. The string is 1 meter long and it's connected to that pulley at the end of the bench. Now if I change the frequency of the generator to something faster than once a second, then something interesting might happen to the string. So here it is on 10 hertz, 10 vibrations a second, and nothing particularly interesting is happening to the string yet. So let's increase the frequency up from 10. Now, there we are on 25 hertz, that's 25 times a second. We seem to have got what's called a standing wave. So you can see it's got a node at each end where it's stationary, but the middle part has got a massive amplitude to it. Let's increase the frequency a bit more. Right, now at this point we've got a stationary point at that end and in the middle and at the other end. So this is one complete wave. A complete wave that is 1 meter long. So the wavelength is 1 meter. The frequency is, looking over at the frequency generator, we can see it's 40 hertz. So for this string, this type of string, if we vibrate it 40 times a second, we get a complete standing wave. Now let's increase the frequency a bit more, see what happens. Right, now at this point we've got 3 patterns in our string, on our string. A half a wave, a half a wave, another half a wave. So we've got 1.5 wavelengths trapped on our string with a node at each end and then 2 nodes at a third and 2/3 point. So we've got 1.5 waves here and a standing wave. This is the third harmonic. If you've ever done music, you'll know this is how strings vibrate on stringed instruments. Let's increase the frequency a bit more. That is at 55 Hertz. Let's go higher. Now we've got 2 complete waves. So we've got 4 patterns. You can see the vibrating pattern fits onto our string 4 times. So we've got a wave going through to the middle and then another wave going through to the end. So we've got 2 standing waves this time and our 4th harmonic. The frequency now is 70 Hertz. Let's increase it one more time. Yep, it is there, although our string, the quality of our string can't quite handle it, but we have got 1, 2, 3, 4, 5 stationary points. So we have got 2.5 waves trapped on our standing wave string. And that's at 90 Hertz. I think if we go higher we won't see any more, but we'll try. Oh, nearly there. Yeah. Half a wave, 1 whole wave, 1.5, 2 whole waves, 2.5, 3 whole standing waves on our string. And it's vibrating at 110 Hertz. Let's return to our 40 Hertz wave. You can see that stationary point in the middle there, and we've got a stationary node on this side here, so we've got 1 complete wave from one end of the string to the other. Now let's have a look at the amplitude of this wave. Normally people think that it's from the lowest point to the highest point, but that's not true. The amplitude we describe as being from the center point to the top, or from the center point to the base. So it's really from this point here upwards. That is the amplitude there, and that's the negative amplitude there. So if you say what the height of a wave was, you're going to measure it from this equilibrium point, not from how deep it goes. If you set up a bowl of water or a tray a bit like this full of water and use a pencil as a dipper, then you can splash the water and it will create a circular wavefront there. You see it? And if you set your dipper to dip once every second like this, you can see that we've got a frequency of 1 Hertz, and you can see how far apart those ripples are. How far apart they are is the wavelength. How many ripples there are in a second is the frequency. So if I dab it in a sort of 5 times a second, I've increased the frequency and I've decreased the wavelength. Can you see that? The wavelength is now shorter. We can sort of estimate it. I want you to try this and see if you can work out a frequency, say 10 times a second if you can do it that fast, and estimate what you think that wavelength is. I think mine's about 15 millimeters, 1.5 centimeters. But I'm not taking much care with it. You can probably do it a bit better. See if you can see what that wavelength between those ripples is. That's the wavelength. And how fast you dip it, that's the frequency. And we're going to see what the relationship is between the two. You might have guessed already.